Welcome back. A few weeks ago I made a video about the basics of using such a QMC5883L 3-axis digital compass with an Arduino. In that video I used an existing library to interface to my Arduino Nano here, and we talked about the 3 axes that these thingies actually cover. These are not the axes I would be expecting. We also talked about the need of calibrating these things for proper usage, and we calibrated mine and we actually got real good compass readings out of it. Card here, link in the description. Now it's time for the details, at least part 1, in which I want to write a library for that thing, our very own library, that is more to my taste. Enjoy! Before we start, one short disclaimer. I'm just a dwarf standing on the shoulder of giants here. There were 6 guys before me who implemented libraries for that thing. I'm just a runner-up, and I'm greatly benefiting from the work they've already done. With that out of the way, let's dive in. Now, before we start implementing an I2C library for that thing, we should have a look at the datasheet and look at its registers and see how it ticks. There are obviously 6 1-byte registers here holding the data of our 3 axes. The data of each axis consists of 2 bytes, a least significant byte and a most significant byte. And these 2 bytes form a 16-bit integer in 2's complement. So with a value range from -32,768 to 32,767. But the next register, called status register, holds 3 bits which are really important when interpreting that data here. The least significant bit in that register, data ready, is set when all 3 axis data is ready, and it's reset to 0 by reading any data register. So we don't need to bother reading all 6 data registers when we have a 0 in here. The next bit, overflow, is set to 1 if any data is out of range. So again, if that is set to 1, we don't need to bother to read the data registers. The last bit, DOR, data skipped, is the most complicated but fortunately also the least important for normal applications. It's set when you don't read out a measurement from the chip via I2C, meaning the chip takes a measurement, you don't read it out, and the chip takes the next measurement. Then that bit is set, indicating that you skipped a measurement. But the bit is also set when the chip is prevented from writing the result of a new measurement to the 6 data registers because you are currently in the process of reading those registers via I2C. That's called data protection. We'll talk about that later. And it's of course done so you don't read the first 3 bytes from the previous measurement and then the next 3 bytes from the next measurement. Next, we have 2 registers here that hold the temperature. Its 2 bytes hold again a 16-bit 2's complement integer, and the gain of the sensor is factory calibrated. However, the offset has not been compensated, so we don't really know where 0 degrees is. We only get relative readings, and the temperature coefficient is 100 lsb per degree C. Of course, there are also control registers, 2 of them. The first one holds 4 2-bit fields here, and the second one holds 1, 2, 3 flags. The first 2 bits in the first control register define the mode of operation, which is either with 00 standby, so the chip really does nothing, or 01 continuous. The next two bits define the output data rate, which can be either 10 Hz, 50 Hz, 100 Hz or 200 Hz. Meaning, for example, at 50 Hz the chip does 50 measurements per second. Then we have 2 bits defining the full scale of the measurement range. That is either 2 Gauss for 00 or 8 Gauss for 01. Finally, we have 2 bits defining the oversampling rate of the internal digital to analog converter. That ranges from 512 for 00 to 64 for 11. The first bit in the second control register is interrupt enable. If it's null, then the interrupt pin is enabled and you get an interrupt signal every time new data is available. If it's 1, that pin is disabled. The 6th bit is the roll pointer flag. Normally it's 0, but when you set it to 1, it enables the pointer roll over function. When you read registers from such a chip via I2C, the register address is automatically incremented one by one, so you're reading the registers in sequence. However, if you activate rollover, then it reverts to register 00 after you read register 06. So you're continuously rolling through the data registers. The 7th and last bit here is the soft reset flag. Normally it's 0, but when you write a 1 to it, the chip performs a soft reset and restores default values in all registers. The last register is the set reset period FBR, which is kind of a mystery. The datasheet doesn't say much about what that register does. This is the only information available about that register in the whole datasheet, and it says set reset period is controlled by FBR bits 7 to 0, so the whole 8 bits. It is recommended that the register 0B, so our set reset register, is written by 01. Probably meaning if you write that register, you should just write a 1 in that 0 bit here. But what it does, no idea. Now, how could the architecture of a library for interfacing with a QMC5883L look like? From a software perspective, that chip is really just a bank of registers you can read and write from via I2C. So why not have a copy, a shadow copy of these registers within the Arduino and then have some methods here in the library, write stuff and read stuff to keep that copy in sync with the original. The whole bit banging necessary to manipulate these registers can be hidden away by some methods here that write just to the or read just from the registers. So we could have a set of get stuff and set stuff methods here for the readable and writable stuff inside the registers. Some just stuff methods that are really functions and give you read-only stuff from the registers, and some action methods that set write-only things inside the registers. With that architecture, errors can really only happen when we do I2C stuff with the write stuff and read stuff, too much stuff, sorry, methods here. And we can have a last error method to retrieve informations about the errors that happened. Add a constructor, an Arduino typical begin method and maybe a reset method, and we're done. Obviously, that architecture also has a drawback. For most things, you will have to do 2 method calls to the library. For example, first a set stuff and then a write stuff, or first a read stuff and then a get stuff. Of course, there are other architectures that don't have that drawback, but they have others. And, well, I want to go with that one. Let's write some code then, shall we? So I have here the first version of my sketch, QMC5883L version 1, consisting of the sketch itself, a CPP file for our library and a header file for our library. How to use header files and CPP files within a sketch, I explained that in detail in the last Making Sense of NMIA 0183 messages video. Card here, link in the description. That first version will only handle the I2C communication stuff and the config registers of the QMC5883L, but this will be enough, believe me. Let's start with the header file for the library. Of course, we include wire.h here, which in fact defines a class named toWire for I2C communication. Then we have our class QMC5883L. Please note, I do not have any type defs outside the class. Inside the public area of the class, I have first a lot of enum type defs, uint8, that is bytes, for the different options inside the config register. And you can see here the numeric values for the members of these enums are exactly the bit pattern of the options. Slight exception here, there is no type def for the interrupt disabled bit, it's just a bit. Then I have a struct here config that contains all the options we have in the configuration register, so from mode to oversample rate, and then just as a boolean without an enum, the interrupt disabled. This is followed by an enum error that specifies the different kinds of errors we can encounter during I2C communication. Then we have, of course, our constructor here, which gets as a pointer the toWire object, which we will be using for I2C, and a byte address that has a default value, so that argument is optional. Let's go over the public methods real quick. We will go into the detail when we have a look at the CPP file. So we have here a begin method, a reset method, a read config method, a write config method, and we have a whole lot of get methods for the configuration. So for mode, output data rate, full scale range, oversample rate, and interrupt disabled. And we also have a get config here that returns the whole bunch in that config struct. Accordingly, we have a whole bunch of set methods from mode to interrupt disable, and again also a set config setting the whole config specified in a config struct. And last but not least, we have a last error here. In the private section, we first have a whole bunch of static constants uint8, so bytes again, starting with the default address, I2C address of the QMC5883L. Then we have here the addresses of our control register 1 and 2 within the QMC5883L, and then we have here a whole lot of bit masks for the different bits inside the control registers. We have a toWire object here, a pointer to a toWire object, which will do the I2C stuff. We have here our I2C device address. Yeah, both are set by the constructor, remember. Then we have here our shadow copy of the QML5883 registers, also an array uint8. And finally, a last error variable, which is obviously returned by the method last error. Finally, we have the private methods doing the actual I2C communication, and that would be read registers, write registers, and write register, singular. The CPP file of our library. So of course I first include our header file and then I initialize all our static constants. I haven't mentioned that before, but I made these constants static so they would only exist for the class itself, not for every object of the class. Then we have our constructor here, which gets as an argument a pointer to the to-wire object and the by default address. Remember, default address has a default value, so that argument is optional, and the constructor does nothing else than initializing our private members accordingly. Currently, begin just calls reset, and reset sets inside the control register to the bit soft reset, sends that register over to our little chip, and then does a read config. Should any of these actions fail, that is, return false, our method returns false, otherwise it returns true. And we pass that up here in our begin method. Of course, if we encounter here an error, we can retrieve it via the last error function. Then we have readconfig, which we already used in reset, and writeconfig. These are primitive affairs. Readconfig really just reads the two control registers, so starting from control register 1, 2 registers from our chip, and writeconfig writes starting from control register 1, 2 registers to the chip. Both, of course, return true when they are okay and false if something goes wrong. Retrieve the error with last error. That is followed by all our get methods, and they work all the same here. I just take the right register and I binary AND it with the right bit mask and return the result. And finally, we have our get config, which just uses all these get option methods here to fill up a config struct and return that config struct. For every get method, we have, of course, a complementary set method. The bit banging here is a little bit more complicated. First, we take the current content of a control register, then we binary AND that with the binary NOT of the bit mask for that option, masking out the bits of that option, and the result we OR to the option we want to set, and the result is of course written back into the register. Set interrupt disabled is working a little bit different. Here we get as an argument, not a bit mask, just the boolean. If the boolean is true, we set the register to the bit interrupt disabled mask, otherwise to 0. We don't really care about the other bits in that register. setConfig gets, of course, a config struct here and uses the already implemented methods here to set all the bits in the two control registers. That leaves us with the last arrow method here, which just returns the last arrow member variable. Before we dive into the read registers I2C stuff, let's have another look at the datasheet. There's a very nice picture here in the datasheet of the QMC5883L illustrating how reading data from the chip via the I2C bus works. And I've hand colorized it here for your convenience. So yellow is stuff transmitted by the master and green is stuff transmitted by the slave. The master starts by transmitting start and then the slave address followed by a read-write bit set to 0, meaning we want to write some data to the slave. And the slave acknowledges that, and the master writes the register address it wants to read to the slave. That's also acknowledged by the slave. Then the master sends again a start and again the slave address, but this time the read-write bit is set to 1, indicating we want now to read data from the slave. The slave acknowledges and sends the data from that register. If the master sends now an acknowledge, the slave sends the data from the next register, and so on, until the master sends a not acknowledged, which causes the slave to stop sending data, and finally the master sends a stop signal, releasing the bus for other devices. So, The read registers method gets as an argument the address of the first register we want to read and the total number of registers we want to read, starting with that one. We have a local variable status here, and first we do a wire begin transmission with the I2C address of our chip. That just queues that byte here of the device address set with the read bit to 0 into the output buffer of wire. Then we do a wire write with our first register address that also just queues that bytes into the output buffer. And then we do a wire end transmission here. And that actually sends the start signal on the bus and sends these 2 bytes out. And because we have here a false as an argument, it won't send a stop signal after that transmission. However, it returns a status. And if that status is not 0, something went wrong, and we write that status into our last error variable. Please note that the numeric values of the first few members inside our enum error are exactly the error codes returned by end transmission, so that's okay. Should we encounter an error, we exit the function and return false. Otherwise, we do a wire request from, again with the I2C address of the device and the number of bytes we want to read from the device. Remember, we already told the device here from which register on we want to read. We also pass here true as an argument, meaning after the whole reading cycle is over, the master will send a stop on the I2C bus and release it. The bytes returned by our slave are not directly available here, but again written into an input buffer of the wire object. However, the wire object here returns the number of bytes actually received from the slave, and if that number is not equal to the number of registers we want, we again throw an error here, this time I2C request partial, and exit the function returning false. Otherwise, we use the wire read bytes method here to retrieve the bytes from the input buffer of the wire object. And that gets as an argument a pointer to a byte array. In our case here, the base pointer to our registers array, plus of course the first register we are reading, plus the number of bytes we want to retrieve from the input buffer, that is the number of our registers. That read byte method also returns the number of actual bytes copied from the input buffer into that array, and if that number is not the number of registers we wanted to read, we throw again an I2C request partial error and exit the function returning false. Otherwise, we return true and we are finished. Before we go into the details of the write registers and write register function here, we have another look into the datasheet. There we find another nice graphic illustrating what's going on during an I2C write, and I also have hand colorized that for your convenience. Yellow, the stuff sent by the master, green, the stuff sent by the slave. And here we also start with a start signal from the master, followed by the slave address with the read-write bit set to 0. That's acknowledged by the slave. Then the master sends the register address which we want to write to. That's acknowledged by the slave, and then the master sends the data that should be written into that register. Also acknowledged by the slave, and then the master sends a stop signal, releasing the bus again. Let's start with the write register singular method that actually performs that I2C write transaction. It gets as an argument the register address of the register we want to write, and it also has this local status variable. We begin again with the wire begin transmission and the device I2C address. That's just queued again into the output buffer with the read bit set to 0, nothing new. Then we write the register address we want to write into the output buffer, and finally we write the content of that register into the output buffer. And then again we do a wire AND transmission, and this time we give here as an argument true, meaning after all that I2C stuff happened, we send a stop to the I2C bus and release it. We have the same error handling here like before, and if no error occurred, we return true and we're finished. Now let's have a look at the write registers method, which is of course a complement to the read registers method, and as such gets the first register we want to write as an argument and the total number of registers we want to write, starting with the first one, of course. We have a local variable register address here, which we loop from our first register we want to write to the last register we want to write. And to write that register, we use, of course, the write register method. And should that call fail, we exit the function and return false. Otherwise, we're done and we return true. That leaves us with the sketch itself, and of course we include wire here and the header file of our library. Then we instantiate a QMC5883L object, just passing pointer to the wire object here and relying on the default I2C address. Within the setup, we initialize our serial and we wait until our serial is ready. Then we do a wire begin and set the wire clock to 400 kHz. That's the maximum our chip can handle. Then we do a begin here, and should that fail, we print out the error. Then we get the config. Remember, begin already does a reset and a read config, and we print out that config. Then we set the configuration to the following parameters: mode continuous, output data rate 50 Hz, full scale range 8 Gauss, and oversample rate 256, interrupt disabled true. Then we write that configuration to our chip. Should that fail, again, we print the error. Otherwise, we read the config back from our chip, just checking here if everything works. Should that fail, we print out the error. Otherwise, we get the config again and print it out again. We have absolutely nothing in the loop, and print error really just prints out the error on serial. And print config really just prints out a config struct nicely formatted here on the serial port. And that's the output on the serial port. So obviously no errors, but two configs. So the first config is the default config of the chip after the reset. And mode is standby, output data rate 10 Hz, full scale range 2 Gauss, oversample rate 512, and interrupt disabled false. Then in our code we set the config and we write the config and we reread the config back from the chip, and so the second config contains continuous, 50 Hz, 5 Gauss, 256 and true. So everything's working fine. And on that note, I will leave you for today. I know, a bit anticlimactic, but we already done the heavy lifting now with the I2C communication, and that's obviously working fine. And the next time I will read whatever information I can read from our little chip here, and we'll see what we can learn about it. Anyways, from there on, we'll just have to play it by the ear. So, till next time, bye!